Hello, I'm Emma Gaidova,
And I'm Elena Popovska.
and we are from North Macedonia.
Our project is the potential in biodegradable film obtained from whey protein.
Today, more than ever before, we feel the effects that plastic has on our health and our environment. One major environmental issue we face today is overflowing landfills with plastic waste that has the potential to spread diseases. Finding an adequate alternative for such plastics can sometimes be expensive to implement or create.
Many raw materials have been proposed as possible alternatives, such as first-generation feedstock. This includes crops and plants that are used to produce bioplastics. However, they take away food used for human or animal consumption. Therefore, the preferred type of raw material is second-generation feedstock. This is not edible biomass, meaning that it is usually waste, byproducts, or residues from other processes. One such material is liquid cheese whey.
Liquid whey is the byproduct of cheese production. After the two main stages of the cheese-making process, which are acidification of milk and coagulation of the milk curds, the third stage is separation of solid cheese and liquid whey. Casein protein and whey protein are the two types of protein present in milk. Casein constitutes around 80% of the milk protein, while the remaining 20% is in the form of a whey protein. Unprocessed whey is a yellowish liquid with a sour taste. It contains proteins, lactose, and minerals. Some of the minerals include zinc, iron, copper, and magnesium.
During cheese production, 9 parts of whey are generated per 1 part of cheese manufactured, and yet, despite its mass production, it is seen as a waste material rather than a product itself. Approximately 50 million tons of cheese whey is produced in Europe annually, and although some of it is used in the bodybuilding industry, roughly 40% of it is discarded directly into the environment. This is not only a waste, but it could in fact be toxic. When disposed into soil, it creates a subsoil layer of fat restricting plant growth, while when disposed into waterways, its high biological oxygen demand results in the lack of oxygen necessary for the living organisms that reside there.
Yet there is a possible potential to it. It can be used as a raw material for producing an alternative biodegradable biopolymer. After extensive research, we discovered that all was necessary to achieve this were liquid whey and some non-toxic chemicals.
Osugovska Mlekara, which is a local dairy farm in the village of Sokolarci, not far from our hometown Skopje, was happy to give away their excess whey to us. We started research in late September, and by the 13th of October, the chemicals, which we had purchased from Varus, a local chemical supplier, arrived. We started experimenting the following week. Those chemicals which we had purchased were tetramethyl diamine, also known as TMED, a polyethylene glycol, also known as PEGMA, ammonium persulfate, and methacrylic anhydride. The whole process for creating whey protein plastic consists mainly of 5 stages: processing liquid whey, methacrylation, copolymerization with PEGMA, addition of thiamide and ammonium persulfate, and finally the drying of films. We first began by processing the liquid whey into powdered whey. We vaporized pure liquid whey by heating it for 4 hours, resulting in a solid whey protein concentrate, which we then dried and pulverized.
We made 2 attempts in creating powdered whey concentrate. In the first attempt, we heated all the liquid whey for a longer time until it vaporized, which naturally resulted in a more protein-packed powder, losing more of the whey nutrients. In the second attempt, we heated the whey for a shorter time, periodically removing some of the top layer of liquid, and the resulting powder was more nutrient-packed. For our experiment, we chose to use only the whey protein concentrate powder from the first attempt. Although it lacks nutrients, it contains more pure protein.
Although the main purpose of heating the whey was to obtain powder using our limited resources, heat also has an effect on whey protein structures. Whey proteins are globular proteins, which means they're spherical. With heat, they can be remodeled to become linear, enabling polymers to later form. The second stage of our process was methacrylation. Methacrylation is an amide-based reaction. The reasons for methacrylating the whey powder is to chemically activate its proteins so that they can later bind with pegma. With a pipette, we added 1 milliliter of methacrylic anhydride to 20 grams of whey protein concentrate powder. We placed the mixture in a magnetic stirrer at room temperature for 18 hours. We poured each of the resulting mixtures between two separate pairs of parallel glass plates and let them stand at ambient conditions for 2 hours so they would form gel-like sheets. We then peeled off these sheets and dried them at 60 degrees Celsius for 46 hours in a dehydrator so they would form elastomers.
Finally, plastic films formed. The 30-70 ratio plastic was more flexible, had greater tensile strength, and was softer in texture, whereas the 40-60 ratio plastic had greater density, yet it was more brittle after drying, which makes it prone to breakage. Therefore, the 30-70 ratio plastic proved to be the optimal ratio. During the development and execution of our project, we faced numerous challenges, which we were able to easily overcome through teamwork, honest communication, and cooperation between each other and our mentor. Our first challenge was researching the topic, since there are very limited resources in our particular topic, as well as purchasing the necessary materials, for they aren't produced in our own country, and had to be imported from countries including Germany and Japan. In our first attempt, we had gotten the ratios of whey protein concentrate to pegma incorrect, and this led to us reevaluating our calculations and correcting our mistakes. This only helped us better understand the chemical processes and how great of an impact proportion has.
We also had a difficult time with figuring out the degradation time, for we lacked the proper controlled environment to give any specific duration. We can only estimate that the degradation time is between 1 to 2 months when it is left out in soil, while it could be longer in an indoor space. Finally, we didn't have the advanced technology necessary to conduct proper lab analysis of both the physical and chemical properties of the material. These protein films could very well replace conventional plastics. It is estimated that the production of biodegradable packaging will grow by 20% over the next few years, taking up a larger share of the packaging market. The European Union dairy industry would also benefit from the increased income and having a long-term, secure disposal route of their whey, which is essential for avoiding environmental risks.
The average price of polyethylene-based plastic is 0.42 to 1.26 euros per kilogram, whereas the whey protein concentrate average plastic price is 2.94 euros per kilogram. When choosing an eco-friendly technology instead of one that emits a greater amount of greenhouse gases, there is usually an additional cost to the manufacturing process. However, with further research and development investment, this amount can be lowered. The high cost also does not take in account the long-term positive effects on the environment, as well as profit for utilizing a wasted resource.
In the future, whey plastics could be used in many forms and ways. A range of whey plastic packaging and objects can be obtained using different post-processes, including lamination, thermoforming, and thermosealing. This way, whey plastic films could be available in tubes, laminated cans, trays, films, blister formats, and many more. Also, based on pegma's excellent oxygen barrier properties, whey protein concentrate films could someday fully replace EVOH nylon or polyesters, which are generally used for their oxygen barrier.
Whey plastics are also sterile. Whey contains immunoglobulins and glycomacropeptides, which help prevent bacterial infections. Pegma is a polyethylene glycol, which makes it a proper copolymer for a bioplastic, since it does not trigger an immune response. Oxidation-sensitive polymersomes, such as pegma, are also used as nanocarriers for antigen delivery. Whey plastics are also antimicrobial and good oxygen and humidity barriers, which are critical for maintaining the initial quality of the packaged product. Perfect for medical and cosmetic packaging. The properties of whey plastic also make it optimal for food packaging, as it can keep food fresh for longer.
To conclude, with whey plastics, we can find a new commercial use of the currently discarded cheese byproducts. We can also replace petroleum-based plastic with recyclable bioplastic that also possesses the same mechanical properties. Whey protein concentrate plastics have a versatile use for food, pharmaceuticals, and cosmetic packaging. Their antibacterial and antimicrobial properties from the whey, combined with the excellent oxygen barrier properties of pegma, result in a plastic that is a sturdy, safe, and sterile alternative to many synthetic plastics. Thank you so much for your time.
If you have any questions, feel free to contact us via email.
We would also like to thank Varus for providing us with all the necessary chemicals, Osugos Kumekara for providing us with pure liquid whey, and Yahya Kemal College for allowing us to use their laboratory during the conducting of our experiments.